everyone. So today is second day of Kinetics, and God knows we've only got, what, 3 or 4 more classes left. Final exam aside from that, and of course the final exam review. Final exam review, I will have 2 hours straight. I'll break them up into 2 videos, obviously. That'll be a heck of a thing. And I'll have that on Friday, and the final exam is usually on the Wednesday of exam week, so not a huge amount of time. I'll try to do it early, like I did all the other times, so heads up on that. Kinetics, of course, will be on there because why do any of this if it's not on the final exam, so expect that. So I guess there's not much else to say aside from review what we did last time. Now we're gonna have to be careful here because I know I told you some things last time that made you think that these rate things, these kinetic equations worked a certain way, and they don't. So to explain, let's review what I talked about last time. We'll do a simple reaction, A goes to B. And the rate, of course, is the change in reactants over time. Again, I like to try to cast everything in terms of a reagent, not a product. Reagents are the things I always control, at least initially. So I like to say rates are proportional to minus the rate of change of reactants. I don't have to do it that way, but I usually do. Now, this is called a rate law, by the way. I said that a couple of times, but I didn't define it. And I didn't do that, so I didn't want to overwhelm you with a whole bunch of random facts to try to memorize. But this is called the rate law. And it just expresses the derivative in terms of K and concentration. Now we talked about why concentration, for a reaction like A goes to B, A is the actor responsible for the transformation. This is like an isomerization, just an example of what works that way. A is responsible for the action, and it only takes one A. It's doing it on its own. So the rate is proportional to the concentration of the things doing the action. So this is first order. So we've raised concentration to the first power using some really first semester calc. I mean, everything I hope has been first semester calc. Using first semester calculus, little integration, we get that the change in A is exponential in time. So real simple stuff. Okay, next bit. Again, with the idea that the probability that something occurs is basically what a rate is. And it would be proportional to the actors that are responsible for said action. In this case, 2 A's. An A has to meet an A in solution to react. Remember, that's called autocatalytic. That's scary. When things react with themselves, that's scary. Trust me, there's all kinds of examples of things that do that. They usually go boom. So these are well-known things, and they're scary. So the rate law is now going to be proportional to A squared, because it takes 2 of them to react. And then, again, first semester calculus, we're able to solve for A as a function of time, and that's called an integrated rate law. So rate law, rate expression, integrated rate law, integrated rate expression. You'll hear the same terms. I won't hold you to memorize that this is the rate law and that's the integrated rate law. I'll spell these out for you. Okay, now here's the thing I mentioned to you that I know I was making you think that something worked a certain way and it wasn't really true. What that was that this coefficient is the same as the power, the order of the reaction. So there's a 2 in front of the A, and so I have a concentration of A squared in the rate law. I know I led you to that conclusion, but it is not necessarily true. Now I know you'd rather hear it is true, is not true, is not necessarily true, is the worst thing you could hear. Because now you have no idea. And that's true. Here's why it's not necessarily true. It depends on how you interpret what I wrote. Now, you are quite used to seeing chemical reactions as being reactants go to products. But now, think about this. What goes on in your mind if you are visualizing this reaction occurring? If you do it the way I was describing, an A meets an A, that is actually the mechanism of the reaction. So when you see this kind of information, two molecules of A form a molecule of B, you have to ask yourself, is this just products reactants? Or is this a statement as to the reaction mechanism? Because those may or may not be the same thing. Here's my point. What if two A's form a C that turns into a B? That's different. And it may not be true. All the rest of the stuff may not be true as a result. So the rate law, the order depends on the mechanism. The mechanism, not just what products and reactants are. And again, one of the reasons that this gets complicated is when you see this information, you may or may not be seeing information about here's just products and reactants. That's always a safe assumption. It could be true that two A's directly form a B, in which case that is the same as the mechanism. What you may not be seeing is if two A's form something else that turned into a B, and if that's the case, and you're not being told that, then you actually don't know how the rest of this kinetic stuff goes. Right? And I hope that'd be obvious. I mean, imagine if two A's form a C, and C takes 1 billion years to form a B. Right? Well, then all this rate stuff would be completely different. Of course it would. So that is something you've got to be extraordinarily careful with. When you're told something, is this the mechanism or just a statement of products and reactants, which is generally what you've been seeing most of your education. It's just a statement of what reacted to what. Now I'll give you some more examples to delineate between the two. So I know that's like, well, how do I know what's what now? I will show you examples to make that more clear. But anyway, so that's the problem. The good thing is that, now remember last time we also talked about figuring out these orders of reaction, how you make like a log plot, a log of rate log of the reactant concentration and the slope of the line. Remember that? It was at the beginning of last lecture. The good news about that is that that number tells you about the mechanism. Here's the big picture. Now put a star by this. Kinetics is important. For one, I gave the example of like someone running a chemical plant, making sure that it doesn't blow up. Okay, that's pretty important. But what personally, as like an academic, I would care about is that these orders of reaction tell you how the reaction occurs. So if you want to know the underlying mechanism, you have to do kinetic analysis. And understanding how things occur is the first step towards making them work better. Or, just understanding, sometimes we do things just because we can. We're going to go to Mars really just because we can. I don't know that we're really going to get much out of that other than to prove that we can do it. Sometimes knowing how reactions work means that we can manipulate them to work better with less energy, which is like kind of hideously important right now. So that's the value. And again, the only way to do that is with kinetic analysis. It's actually what I got my PhD in. All right, so that's a big review. So there was a bunch of stars by things. What is kinetics good for? It's good for mechanisms. Mechanisms are revealed in these orders. Orders have to do with the mechanisms of the reaction, not necessarily the statement of products and reactants. That's what you've been seeing your entire chemical career. And I will make some more, I'll give you a really good example of being able to differentiate when you're being told this is just products and reactants versus this is how it's working, because they're expressed the same way. Again, this is just, I scooped in 2 A's and I got a B. Or an A molecule met an A molecule and formed a B. Both those stories are told by this. but they could have very different interpretations because, again, if this is just products reactants, maybe there's an intermediate and you're not being told that, but you would if I write down the mechanistic steps, and those are called elementary reactions, and I'm going to write that, I'm going to give you an example in a minute. Okay, before I do that, okay, this is, remember I called this an autocatalytic reaction, a reaction that reacts with a chemical that reacts with itself. Terrifying. I've had one time I made, God, what was it? Trimethylendium in my lab. Trimethylendium. Autocatalytic. It blew up. No one died or anything. It blew up a piece of glassware. We never touched that stuff again. Okay, so these are scary. They do exist. I've even seen them, but we try to stay away from them. Most reactions are like this. They are A goes to B and forms C. Now, even when you see, like, especially like in geology, when you look at geochemical reactions, they're like silicate plus calcium plus magnesium plus SiO2. I mean, they can be unbelievably complicated. Those usually are statements of products and reactants, and the mechanisms are more complicated. The mechanisms are usually multiple steps, but the individual steps, the elementary steps, almost all look like this. It is very rare that, complicated reactions have multiple steps, but the individual steps almost always look like this. So, what's the rate law for that? Okay, now again, the rate law is going to be, it's for the rate. It will always have a rate constant. You have to have that. You got to make the units work. And then you put down the actors. Now this is an expression of mechanism. And it's also the reaction. It's also a statement of what happens. Now since this is a statement of mechanism, it means an A meets a B. That means the rate law is going to be A to the first power and B to the first power. Okay, and as usual, this of course is still the rate of change of A or B, but I'm just going to pick A because it doesn't matter. Okay, now we do our calculus and solve for this. Solve for the change in A or B or C. Actually, I probably am going to want to figure out C. But get this. I mentioned this at the end of the last lecture. As much as this is still a second order reaction, you can tell because the K has the same units. Let's see, this is molarity per second. This is molarity squared, so K is per mole per second. The K here is the same. It's per molarity per second. So these are both second order reactions. Again, you can tell because the K's have the same units. Okay. Oh God, I forgot what I was talking about. This one, the integrated rate law, again, this was very simple. It's so simple I'm probably not even going to put it on a test. You'd just be repeating what I did in class anyway. And you would think like, oh yeah, well this will be easy too. Yeah, it's not. You can, I believe the derivation is on Wikipedia. You can look it up. You have to do some kind of sophisticated math tricks. It takes a while. When I took this class, the guy did it. I don't feel like it. I've been blabbering about some other stuff, right? So I kind of wasted a lot of time. Here's the solution. Again, as much as this was second order and this is second order, solving this is actually surprisingly way more complicated. And get this, you're going to get kind of a way more complicated, way more complicated result. Sorry, I lost track of time. Okay, there's the change in B, and it's divided by its initial concentration, and then you have the same for A, divided by its initial concentration, and that is equal to the difference in the initial concentration of A and B. And it's arbitrary, of course, what A and B are. So, KT, there we go. Okay. So, in brackets, sorry. Okay, now there's actually nothing else I can do with this. This is as good as it gets. It's kind of unsatisfying. And as I mentioned before, to actually, you know, if I'm I'm writing a paper on this reaction and I'm trying to express this information, I express in the paper its second order, I give the rate constant, and there you go. A person competent can repeat this, and at this point you can see why they want to use a computer, and they can plot their products and reactants and whatnot changing over time, and know how long this will take to get their products before they have to be sold, or if they're afraid that too much heat's going to be generated and it's going to blow up. You can see that, you know, the information's in here, but yeah, it's a little bit hard to plot it, and you definitely want to use a computer at this point, something a little better than Excel, right? And so there's really nothing else to say about this. This is the end result. Now, it turns out that because of how complicated this is, notice this. Let's say that, you know, in a reaction like this, I might be tempted to have A and B have equal concentration. If you did that and you're trying to figure out the rate constant, you actually couldn't. Notice that? Because this would be 0. And that means that you can't figure out the rate constant. It's like this weird problem with this type of reaction, which is, of course, the most common reaction. So, guess what? Whenever, you know, people don't really study reactions so much just for the rate data. We did back in the 50s and 60s when it was like kind of discovered that we could do all this. And this one, you have to treat a little different. To get the rate constant, you have to do something called, pseudo first order conditions. Okay, pseudo first order condition. So again, you're writing a paper and you're trying to tell people how this works, and it's tempting to make A and B equally concentrated. That would make sense, but you know what? You're not going to be able to figure out the rate constant. So you're going to use what's called pseudo first order conditions. And you're going to hear this if you work in the chemical industry. You're going to hear this all the time. And what that means is you use excess B. Now that means B at time equals 0. So like 1 to 10, something like that. Now the reason you would do that is that the change in B over the initial, it just basically doesn't change. It's just basically 1, right? Because it'll start at 1 and it'll go down, but it won't go down too much. And this guy will change a lot. Now, in that case, what you have is natural log of 1 over concentration A is a function of time, divided by A that you scooped into the reactor is equal to, here's the next thing. What you're going to do is you're going to also call this thing here, this difference, you're going to call this K prime. Okay, so this difference in concentration times the thing you're actually looking for, you're going to call that K prime. And so, so this difference is equal to, yeah, K prime. Okay. Now, what you do is do some algebra. And I'm not going to do that because, again, you're technically grown-ups. You're out of college in a few days. You realize that? In college, you're a few days. And, you know, one of the things, you know, I shouldn't be talking about this, but one of the things that kind of killed me when I was your age is you're out in the world and you're working your first job. No one cuts you a break. Why would they? No one gives you a break for being new. No one gives you a break for being the first person, for this being your first job. They'll expect you're going to be working with people right next to you who've been there like 10 years. And you're on equal footing. You're not, but they're going to treat you like you are. It's kind of cruel. But that's the world. Now, the reason I'm saying that is I'm not going to do this algebra for you. You should be able to do algebra. So the answer is that under pseudo first order conditions, you get a first order result. The change in A is equal to the initial concentration e to the minus k prime t. So again, what you do to analyze this thing is you, sorry, I gotta keep track of time. You have this situation, you're gonna have excess B. You'll see an exponential decrease in the other reagent, and that rate constant you can get from a linear fitting using some software. You get a result, and then to get the real rate constant, the one that you want. So this is from your experiment, and then you're going to divide that by the initial concentrations. And that is what you would report in a publication to express how this reaction works. Okay, so, and in terms of second order reactions, I'm done. There's really nothing else more to talk about. There's nothing else to talk about. Except, what could I do? I can start to make these mechanisms more complicated. And that's exactly what I'm going to do. Okay, so I'm going to do things like A goes to B, but B goes back to A. I'm going to do A plus B goes to C, and A plus B goes to D. Anyway, you can imagine such complexity. And then you've got to tie them all together to a rate law, and then integrate the rate law to make the integrated rate law. And anyway, we're going to spend a lot of time on that. Now, before I do that, I'm going to give an example of, as I mentioned before, when are you being given information about products and reactants, and when are you being given information about mechanism? Because they look the same, but your interpretation in terms of kinetics, you can only interpret it as if you're seeing the mechanism. And you don't always know that. Okay, so I'm going to give you a dramatic example of how that works so that you get it, basically, right? So I want you to get it. Okay, so here is a gas phase reaction that was studied way back when dinosaurs weren't confined to zoos. And you can see there's really, this is going to be very simple. It, looks like a second order reaction. There's my A, there's my B, and whatever, that's my product. Of course, as I've written these expressions as the decrease in the reagents, but that would be mirrored by the increase in products, if that's what you want to know. So, so there you go. Now, let's look at the rate law. The rate law, which will be sensitive to the mechanism, will be K. And let's see, concentration of H2, right, and H2 has to meet Br2. Right, there we go. To the 3/2. To the 3/2 power. Oh, and I'm not, wait, I'm coming back. See how I keep doing circles? I'm doing donuts. I'm dividing it by Br2. You notice how I put a K1 there? Did you notice that? Here's a K2. Here's a second HBr, the product. There you go. Oops, no, that's ugly. That's not a nice bracket. It bothers me. And that's not a nice one either. There we go. Ta-da! Okay, now, we're in the exam, and I've written this, and I said, okay, here's the rate law. What does that tell you? And you should be able to say, this is a statement about products and reactants. It is not a statement about the mechanism. The mechanism is going to be donkey complicated. Donkey complicated because this rate law is bizarre, right? So remember, the rate law tells you about the mechanism. This is cross-eyed donkey hard, right? That's the correct scientific term for this. That is not reflected in this. This is as easy as apple pie. So therefore, this is not the mechanism. This is not a statement of the mechanism. This is a statement of these are your products and these are your these are your these are your reactants and these are your products. That's all I get out of that. This does not have anything to do with the mechanism. When I know the mechanism, then I'll be able to derive this. So that's how you know, right? Remember I was telling you, I'm going to make it clear to you. How do you know when you're seeing simply reactants and products, and how do you know when you're seeing mechanisms? It's when this should just be a simple second order. It should just be KH2Br2, but all this other stuff means that the actual mechanism is way more complicated. In fact, here it is. Here's how this actually works. Now, I'm numbering things so that because there's going to be a whole bunch of these. And here's K1. Here's another. Now, these are called elementary reactions. And these are all mechanistic in nature. So I'm not just telling you what are products and reactants. I'm telling you how they go. And again, those are called elementary reactions. Now the first three I've drawn here are designed to make the reaction go forward. And I'm giving each one a different rate constant. And let's see here. Now I got two more, by the way. There's 5 of these. All of these make the thing go forward. So what I see here is bromine just breaks apart. I'm not too surprised by that. Bromine is a weak bond. Bromine is not, see, it's not Br2 that runs into H2. It's a Br that runs into H2. Again, you see how it's complicated. Okay, now I've got a product, but stoichiometry says I have an extra H. Okay, just like a Br can run into an H2, an H can run into a Br2, and look at that, now I got more products. So these drive you forward, but guess what? Now you got some that drive you backward. So what can happen is you have some H atoms and they can run into products, and that's the 4th reaction, so that occurs with rate K4. It's really number 2. You notice that? You notice that? It's number 2. This is number 2 in reverse. So this is a reversible reaction. That's what I'm actually getting out of that. Okay, now let's look at, if number 2 is reversible, then guess what? Probably number 1 is too. So what I could do is I could have 2 bromines with rate K5 go to Br2. And these are, so that's number 1 in reverse. And so these are going backward. And that's not that's not good, right? We don't want those. Now notice that this one and this one are, I would refer to these as like unimolecular. And actually this would not be unimolecular. 2 bromines. This is definitely unimolecular. This is just an exponential decay. And the others are a little bit more complicated. The rest are going to be bimolecular, and they're going to be following second order, this and that. All right, next step. So now that I've given you this information, the next step is to write down the rate laws. Now that you know that these are mechanistic in detail, now you can write down the rate laws. And and this is where it gets to be a pain. You're going to have 5 of them. Okay, so now here's, and let me also stop before I do that. Let me give you the big picture here. You've got this reaction, and you do some spectroscopy to study it, and you figure out this rate expression from that data by plotting log, or whatever. You can figure it out. The point of your study is to figure out the mechanism. Now, because you got something so complicated, you know that it's not that this statement of reactants and products, you know that that is also not the mechanism because you wouldn't have gotten such a complicated rate expression. What do you do next? What you do next is you start to generate possible mechanisms, and then you figure out whether these are consistent with your rate law. If they are, then these are bloody likely how it works. So that is what kineticists do. That's how we figure out how things work. Does this match our, this would be like derived from experiment. Okay, and again, that's just big picture. Let me back up and see, now that I know what the elementary reactions are, and I know that these are mechanistic in nature, now I can write down the rate laws. Okay, so the first one, now Br2 is a reagent, and I'll bring that minus sign. Let's see. Here's another detail that I've actually glossed over. We'll spend a little bit of time on this. So there's a lot to unpack on this one. Okay, so I'm looking at this one. This one. Right. Okay, now in our previous examples, I had said that you're gonna take the rate of change of a reactant and you're gonna put a minus sign in front of it. Okay, now that was a good beginning, but now let me tell you a little bit more how it really works. It's a little bit more complicated, although it actually is quite easy. Here's what's happening. This is the rate of change of Br2, right? That's obvious. And notice in the first reaction, it drives its own disappearance, right? Because it falls apart. So that means that I'm going to put a minus K1 Br2. Minus, because this reaction removes Br2. The rate of change of Br2 is going to be driven down by its own self because it's reacting away on its own. Okay, so that's why there's a minus sign there. It's also first order because it's just by definition this is a first order reaction. So Br2 to the first power minus because it's going away. It's a reactant. Now look at number 5. Now in number 5 Br2 is formed. So that means I'm going to have a plus K5. Now the agent responsible is Br. And it takes 2 of them. Now remember, this is a mechanism. Br atom and a Br atom come together. Now I assure you of that. This is a statement of mechanism. That's why you can be certain that you're going to take Br concentration and raise it to the second power. Because this isn't just a statement of how many Br atoms react. It's a statement that one Br finds another Br to form a Br2, which is kind of obvious, right? Okay, so that's how this works. Let me give another example and I'll stop there. There's actually a bunch of these, right? But let's look at the product. I'm just picking that at random. Why not? Let's look at the product. That sounds important. Okay. All right, now, based on the rules of the game I just set up, I'm going to look for where products are formed, here and here. Okay, now in these cases, on the right side, there's going to be positive terms. There's going to be a positive K2 and times things, and a positive K3 times things. That's because these are forming. The rate is going to go up. More HBr is formed over time, plus, because it's going to be plus K2 times something plus K3 times something, because you're forming HBr, you're forming product. Okay, so again, to make that more clear, let me go ahead and just write it down, plus K2. But now what? Well, again, the name of the game is let's look at the reagents, and this is a mechanistic statement, so K2 times the concentration of Br and the concentration of H2. Because this is a statement of mechanism. A Br atom has to find an H2. So this is a bimolecular second order. Okay, the next one is plus K3. And that requires an H to find a Br2. So I just multiply this times the concentration of H atoms and Br2. There we go. Okay. But, now remember, what you have to do is you have to find all the HBRs. These were positive because they're forming, but look at this one. This one, now I'm going to have a minus K4 because this guy is destroying. This is wiping it out. So that means I've got another term. Sorry, I didn't. I'm writing down right. So minus K4. So this is not helping. That's why it's minus. And what are the reagents? H. An H atom has to find an HBr. There you go. And that is the rate law for HBr. Now, what you've got to do, and I'm not going to remotely do this, I'm not even really sure how it's done, to be blunt. You've got to write down a rate expression for H and H2 and Br atoms. So we've got a total of, so isn't that kind of interesting? 5 elementary reactions, and we have 5 different species, Br2, Br atoms, HBr, H atoms, and H2. So we got those 5 things. We have to write those, and then we have to amalgamate them to equate to this. And it would work. It would take pages of algebra, and when we're able to combine all these to derive this, that means that this is the correct mechanism for what goes on. Okay, now again, to continue on, I could write the rate of change at H and H2 and Br atoms, and I could do all the algebra, and it would work out, and I would get here. But no, I'm not going to do that. Screw that. No, I'm not going to do it. It would take like all day. I just want you to know that it is possible to do that algebra. Instead, let's look at some other simple ones. And in the time, I've actually got a fair amount of time left. Maybe I'll end a little early. I will do two more examples. Okay. Instead of this hideousness, I'm going to throw some more complicated reactions at you, one that we can do the math. And I'm going to do that until the end of the semester, which is really soon. And again, I'm going to pick examples that are like kind of obvious, like, well, yeah, I bet chemicals do that. And they're going to be ones we can solve. The end, what I'm going to end with is looking at enzymes, right? You know, that's kind of important, right? Enzymes are a thing, right, for biology. Okay, I need to wipe out the board. Let me do that, and then we're going to just do a couple more examples, and we're just basically going to run out the clock that way. Okay, and we do have a fair amount of time left, so let's think of something that would be kind of obvious would happen, and I even talked about this before, a situation like where you have A goes to, and I'm going to write K1. Now that's actually a way you can know when I'm writing a mechanistic, when I'm making a statement of mechanism, is when I put little K's over the arrows. I could not do that if I'm simply just telling you, here are the reactants and here are the products. If that's all I'm telling you and that's not the mechanism, I would not be writing K's over those arrows. That would not be proper. So when you see me writing K's over the arrows, then you know that I'm describing a mechanism. So this looks like a protein isomerizing to another protein isomerizing again. So that's something I would imagine would happen. And of course we can solve it, right? Okay. Let's start with the reagent. Makes sense. And building up on the game we just played, what you want to do is look at what steps you're gonna have minus K's times things that drive the species down, and you're going to add K times things that make the species go up. Now, in this particular case, A can only decrease, right? And what drives A downward is going to be the first step. So I'm going to have a minus because A can only go down. It's not formed by anything. It just goes away. So that's why I've got a minus. K1 is the one that does it. And the actor is A itself, which is often the case. There's nothing else to add. There's not a subsequent something something. So we're basically done with that. Okay, this is a first order reaction. It's a first order decay. That's the first thing that we study. And I don't need to do any of the algebra or math or calc to know that A of T is the initial. There we go. All right, so done. Okay, now B is a little bit more complicated. And again, so I probably would put on an exam some statement like this, a mechanistic statement, and say, hey, what's the rate law for species B? Okay, again, so I'm glad to be doing this. We're going to do a couple of examples, and that should get it into your head how to do this. Okay, B is formed by the K1 reaction, right? So I'm going to put plus K1 because this step forms it. So that's going to increase the amount of B, right? So that's obviously positive. What is the actor responsible for this? Well, that's A. All right, so again, I hope you see how the game works. Okay, now B is different than A because there's a reaction that forms it, an elementary reaction that forms it, that's A to B, and then there's another elementary reaction that makes it go away, and that's B to C. Okay, so that's going to be, so this reaction, this elementary reaction is bad. So I'm going to give that a minus K2 because that's making the concentration go down. Now what's responsible for this transformation? Why what's the actor? It's B itself. Again, that's almost always the case. So there you go. And we're done. Now we're gonna work further on it, but you can imagine that C is very simple. So of course C is formed, so that's plus, by which reaction? The K2 reaction. What's the actor? It's the concentration of B. So now you have to ask yourself, just like in our various quantum models, what do you want to know? Well, probably you want to know about your product formation, because why are you doing a reaction if you don't want to know about your products? Notice I wasn't really so worried about whether I was looking at products or reactants, because they're really, they're flip sides of the same coin, and those A goes to B or 2A goes to B examples we had before. This one's a bit more complicated, right? So I'm going to try to get towards, I'm not so worried about the loss of reagent as much as the formation of a product. It's more sensible that a person is going to care about product formation as we get to these more complicated examples. Okay, so let's look at this. Here's another thing that drives me nuts, and I just did it. One thing that drives me nuts about all this kinetic this or that. Notice that I just wrote concentration of A. But the thing that slays me here is it seems like I got two of them. Now that I'm in kinetics land, rate expression, integrated rate expression, I have two types of A. I've got A of T and I've got A at time 0. Well, which one is this? It's common not to state, but it's actually A as a function of time. Right? That kind of makes sense, doesn't it? So, because this is like dynamical. If K is a constant and this was A at time 0, and that's like B at time 0, then this is just a bunch of constants, and that doesn't really make sense. If I'm talking about dynamical, why is everything a constant? That doesn't make sense. So again, look out for if you somehow find yourself doing this for a living, like, and I literally do. When you see people write these coupled rate expressions, these rate laws, they often don't make it clear that this is actually, so K1, A as a function of time. Now, I'm saying all that because I actually already know the expression for A as a function of time. It's e to the minus k1t times the initial concentration. Okay, minus. Now notice that, remember this whole little blah, 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 is this A at time 0 or A at time t? Notice that, what about this? What is this? Well, this is clearly B at time, this is B changing as a function of time, and this is B as a function of time. So, in the big picture, this and this are the same thing. So it's kind of like this. It's like dy dx is equal to some stuff e to the minus constants minus another constant. Right, so it's kind of like this. Change in y with respect to x is some, change in y with respect to x is some constant e to the minus x times some other constant. Actually, it's kind of like this. Yeah, to simplify it as much as possible. Sorry, I'm just kind of babbling around. It's kind of like this. Change in y, change in x is e to the minus x minus y. Let's just put it that way. So again, I've hugely simplified it, but I just want to point out that this diffie-q, this first order differential equation, basically kind of looks like this. Now, I'm not sure how to solve this. It scares me. However, you can look in a textbook, you can look online. This is actually something that people run into, this type of thing. And then you just have to throw in some constants. You have to throw in some constants, and that's not particularly hard. Actually, I have some software, actually Mathematica, like what you use online, but like the professional version, the one you have to pay for. And what that means is that, of course, that expression has a standard solution, and so that allows me to write down the integrated rate expression. And it looks like this. It's, I could never imagine that, off the top of my head, I could not look at this and say, oh yeah, well that makes sense. I doubt anyone could do that. Well, maybe Stephen Hawking or someone like that could look at this and say, oh yeah, sure, that's what it is. Again, I either use Mathematica Professional Edition, or again, actually that diffie-q is actually kind of a well-known one. So here you go. So here's what that looks like, and notice that. Remember, I was telling you this isn't really what I want. What I really want is this, the product. Okay, so notice that the next step is to take this thing and plug it in here, bring the change in t over and integrate it, right? So you see what I mean? So what you would do is you would integrate the change in the concentration of C equal to K2 concentration of B with respect to time dt, where B with respect to time is all of this. That looks unpleasant. Turns out that there's another way to do this. All right, so let me point out. God, I have to. It takes me a while to stare at this because it kind of gives me a headache. It turns out that from the plain stoichiometry of the reaction, from the stoichiometry of the reaction itself, you're going to want to make extra notes because it's going to be kind of hard to follow what I'm doing here. The concentration of A plus the concentration of B plus the concentration of C must always equal the initial concentration. And of course, that would be of species A. Now, again, it just kind of makes sense. If you've lost half of this, then you have to have half of that, and whatnot. So all of these have to add up. Now, if that's the case, then species C, and of course these are all, with respect to time. So species C, concentration of C with respect to time is the initial concentration of A minus A as a function of time minus the concentration of B as a function of time. So I'm just saying that there's a trick to this. Now, A as a function of time has already been solved, and B as a function of time is right here. So notice that the point of this is that it's a little math trick because of the stoichiometry and the fact that I've actually already solved A as a function of time and B as a function of time, even though I had to use some crazy software to do it, whatever. I actually already have the solution. It's just I'm going to have to do some algebra. And when I do, it looks like this. So you can imagine A, the initial concentration. What am I doing on time? Yeah, I'll probably end with this. Okay, so one, God, this is actually kind of hideous. Oh God, I can barely even read my own notes. It's kind of complicated. And hopefully I won't mess up a minus sign or anything like that. Okay, so you have that. Difference in rates. Okay. So this is the formation of products, the kinetics of the formation of products. Now, the way that looks is like this. A as a function of t. Now remember, that's a pure exponential decay. I'll dash that one. Okay, now B, the middle species, you have these exponentials that are fighting each other. And what that means is that it's going to rise and then it's going to fall. Like that. Now you can kind of figure this out just from horse sense, let alone all this bloody mathematics, because if A decays, you have to get B. That's the first place it goes. So I'm not surprised to see an exponential decay in A and like initially an exponential increase in B. Exponential decrease in A, exponential increase in B. So I drew B of t. Okay, what's C of t? I've got to label the axes. Well, C of t, of course, starts out at 0, but what happens is B starts to react away, and there you go. Oops, and this just would be, they'd all be the same amount. Anyway. So there you go. A decays, forms B, but B decays to form C. A, B, C. In case you get lost, there you go.